together.
Okay, I think we're going to start.
Yeah.
I think firstly, as today is our second sort of invited lecture, I think it's a kind of testimony, I think, to our jurors to have the kind of stamina to actually accept a lecture to be given after this kind of marathon that we've been on. I think one of the things that's been really important for us anyway is to really bring people from the outside to come and critique the work. We kind of really feel that the DRL is a participant, let's say, in a much larger project, and that extends to practices that obviously are trying to apply some of this stuff and other research institutions and so forth. So I think in kind of extending that hand and also thanking Tom Wiscombe actually for accepting, in a sense, something that he did actually for our studio as well when we went over to SciArc. We feel like there's a kind of synergy in a lot of the kind of work in terms of a kind of active debate. And Tom, I think, is one of the young practitioners who's really trying to really forge a kind of new relationship between research and practice. He's one of those young practitioners, if you want to call it, has put his time into kind of avant-garde practice with his kind of history of working and collaborating with Coop Himmelblau. And I think he's one of those individuals who's quite unique in this case, because I think not only is he sort of trying to project a kind of radical practice, but I think he's built in the capacity to try to realize that when given really the opportunity to do this. So I think it's a very fitting kind of lecture actually to conclude this last 2 days worth of events. So with that, I just keep it very brief. Tom Wiscombe, as many of you know, is the head of emergent architecture, and he's also a professor at SciArc. And if you would welcome him, I think it would be very appreciated. Tom Wiscombe.
Hello? Thanks, Theo. Okay, I'm on. Yeah, we need some lights down here. That's just Okay. Yeah, thank you very much, Theo, and everybody else at the DRL for having me. This has been great. I was just telling Marta that this has been like the most interesting set of reviews I've been to in a long while. So I really appreciate that. And also, I see the AA as a sister school to SciArc, and I'm looking forward to having more feedback between the two schools. We call it West Coast and East Coast in London. I don't know how much truth there is to the differences. Maybe I'll talk a little bit about it. But it's really great to be here. I'm not going to keep you guys too long. I may even skip through a few projects. I know it's been a long time, and I'm also not going to make any promises that I'm going to remain standing during this lecture. I'm kind of out of it, but we'll just do our best. So, I wanted to throw something out there in view of some of the discussions that we had today, but also some things that I came to London with. And that is sort of locating ourselves as architects. Nowadays, we're already through the first phase of the digital. Everyone knows that, where we were just completely enamored by what the new computers could do, form making, and we've gotten into another phase where computations become much more important, where we're much more interested in intelligence in systems rather than just form making, and embedding forms, let's say, with other kinds of systems and other kinds of performance. And just thinking out loud, and at the risk of setting up a straw man, I'll just say that let's say there's the architect working in the lab versus the architect working in the jungle. In the lab, you may find that limited or abstracted inputs often produce unrobust outputs. In the lab, you may find some difficulty in dealing with anomalies. You may think that because the process is computational, that it justifies itself. And you also may find that, particularly in very large scales, that the results of some computational work can be feature-starved, by which I mean lacking in character. And whereas in the jungle, and the picture that goes with that is great. This is actually my father. Uh, if you can believe that, yeah. This is my father at NCAR, National Center for Atmospheric Research, in the 70s. I used to visit him here. This was the data reels, and we had a punch card lab and all that. So anyway, close to home. Also kind of funny that it was a Center for Atmospheric Research, because I consider that to be something that I'm interested in as well, in a different way. So on the right, we have our friend James Cameron and his film Avatar, standing in the jungle. We don't know if that's a virtual jungle or a real jungle or what's actually going on in that picture, but that's why I like it. The reason why I show James Cameron is because I'm very interested in the film business, but that's not why I'm showing this. I'm showing it more because it's a lens of looking at the way an architect can be. An architect, and I think that there's been a lot of discussion today about interdisciplinarity. I think that making a film is one of the most interdisciplinary things you can do. It involves designers and engineers and film crews and visual effects teams, special effects teams, marketing, distribution, all these things, and including economics. And so I think it's kind of an interesting counter model, let's say. Let's say these are two extremes in the lab, in the jungle. I think James Cameron probably operates in the jungle. Let's just say, and some of the qualities of being in the jungle is that it's a messy, cross-disciplinary approach. It may include some computation, but it doesn't rely completely on computation, and it also may involve computation entering the project at certain times, maybe not just at the beginning during the generative phases, but later on. Let's say to characterize a facade or some other kind of building system. It's dependent on uneven conditions on the ground, meaning incredibly context dependent. It's effects driven, and it generates rich features and behaviors at the target scale, whatever that may be. So just float that. A big interest of my office in the last years is in, in synthetic ecologies, which came up today in discussion, and I think I have a lot of open ears to this at the AA, which I'm happy to hear. One thing that I've kind of switched over to since being interested in swarms and agents about 10 years ago is an interest in systems and the agency of systems rather than components. And part of that interest is in going cross-categorical, meaning avoiding just intra-category differentiation. Let's say one version of that would be a gradient, which I actually mentioned today in the reviews, and moving more towards cross-categorical emergences. And the two images are on the left. You've got the Zenuso Olivetti factory, which is a very, very early example of someone trying to embed one system within another. I wouldn't say that it's in a kind of emergence yet, a state of emergence. I would say that that there is definitely a hierarchy there, the structural hierarchy over the mechanical. But in this case, what's really interesting is that you do have the possibility of interweaving mechanical performance and structural performance in a single building. So on the right, a counterexample to that, or let's say an extension of that interest, would be the bloodcomb jellyfish, which is super interesting because it's actually a composite of two different creatures. On the one hand, a bioluminescent bacteria, and on the other hand, a transparent jellyfish. And the way this works is that the bacteria gets access to additional food sources, and it's also protected by the jellyfish, and so it's getting that from the relationship. And then the jellyfish, on the other hand, is getting a kind of stealthing mechanism. And the way that works is that because the predators of this jellyfish are in deep water and it lives at midwater, basically there's a kind of interference pattern that goes on between the color kaleidoscope effects and the water bouncing off, the sunlight bouncing off of the water. So it's a kind of stealthing mechanism. So I would say that the bloodcomb is a kind of emergent third organism, and that's precisely what I would say I'm interested in terms of the integration of systems. Now, just to put up another kind of straw man, the dialectic of efficiency versus the good enough. efficiency is an interesting is an interesting concept. It is used a lot of times as a kind of moralizing statement. Actually, there's a lot of talk recently about minima, about zero energy forms, about the best of all possible kinds of forms, and I think that relates less to the practice of architecture, more to a kind of economic, almost political sensibility. At the same time, it also eternally implies problem solving. I would say the word optimization is not necessarily a productive architectural term. I'm not even sure it is an architectural term, in fact. I don't like it. I think it is used very often by engineers. But I think what they're talking about is saving money and weight of steel, which is, again, not an architectural subject, in my opinion. And then in the last example, the annoying latent formal agenda. I think that efficiency comes with not just an interest in reducing cost and weight. It also comes with an aesthetic agenda that nobody ever talks about, and it really bugs me. In particular, high-tech detailing, which involves a lot of chrome and spider-connected glass and all kinds of things like that, cables, and also slenderness in general. And so I think, I kind of want to call efficiency out right now and just say, another example of so-called efficiency is in the specialization of systems, which is also very annoying. If you look at that image, the funny thing about it is that the guy doing the CMU block wall has the most efficient wall. The guy doing the glulam beams has the most efficient beams. The guy doing the mechanical system has the most efficient mechanical system. But what you get is a kind of Frankenstein of ridiculous performance where one has to penetrate the other, absolute conflictual relationship. And there's no efficiency at all because efficiency at the level of the whole is not present. So the good enough, this is a term from biology, which basically says that whenever you look at a whole system, you can never expect the individual parts to be operating at 100% efficiency. So a whole is always good enough, but it's not the best of all possible. So things you find in nature: excess as a matter of course, redundancy. In all systems you find redundancy, and mutation are critical to robustness of ecologies. You find continuous negotiation. The multi-optimum favors robustness at the level of the whole rather than the part. And within this good enough, you have the ability to state and deal with competing goals in an assembly. Good. So, what is this? This is part of a few animals I'm going to show now. I love animals. This is a vampire bat. Now, what's interesting about this particular vampire bat is that he is not operating at 100% efficiency, but he is absolutely full of effect. This is a vampire bat, and it turns out that bats do this all the time. They usually hunt not by flying in like you see in the movies and grabbing or sucking the neck of a cow. They usually sneak up on all fours in this kind of perverted gallop. So this is my good enough for you. This is the hunt of the vampire bat. I love that. Another kind of good enough, which I'll show you more about in a minute, is let's say a dragonfly wing. First of all, why are there two wings? Hard to track. Why there are two wings? Has to do with lift, but definitely not the best of all possible. The best of all possible would, of course, be a single wing. So you've got redundant wings, already interesting. Then what you have is a dual system of quad cells, which are these ladder-like elements, which have beam-like behavior. And then you have these honeycomb cells, which have membrane-like behavior. And the most interesting parts here are, for instance, right there, where you have a hybrid of the beam morphology and the membrane morphology, and that's what we started to call beam brains in the office. The hammerhead, great example of the layman's misunderstanding of how biology works. I'm sure everyone in this room knows exactly how the hammerhead came into being and why it looks like it does. But I'll just say for the sake of the argument, extremely interesting that the hammerhead used to look like a tiger shark. Okay, a tiger shark is the one with the aerodynamic nose. Seems pretty reasonable. The hammerhead, though, didn't just change slowly over time from, let's say, a bonnethead shark, which has a very small hammer, to a winghead shark, which has a very large hammer. It's in fact the opposite. You find by looking at historical research that the large hammer emerged all at once in a single generation as a mutation to the species. Now, this was not at first, this was a pure mutation. This was not at first an advantageous mutation, which is what I like about it. Not quite clear where it's going to go from there. In particular, the emergence of the hammer pushed the eyes out to the edges of the hammer, which basically turns it into a prey animal rather than an attack animal. Right? Attack animals have eyes towards the front rather than at the sides to look all the way around. So the hammerhead evolved this funny way of swimming like this, if you've ever seen one, so that it can actually see forward. And it also, through other generations of optimization, which is a different kind of optimization, which I think is interesting, not the engineering one, started to evolve different lengths of hammer and lengths of nose and all this based on conditions in different oceans. And it even started to evolve an expanded sense of smell that made up for its lack of vision. So what happened is that the hammerhead became the most populous shark in the sea, which it is currently, despite its mutation. So animals misbehaving. This is the skin of an agamid lizard from the Australian desert. I picked this up when I was down in Sydney lecturing. Really interesting creature. The reason why I'm showing you this is because this is a performative skin on some levels, and I'm sure on many levels, that cannot be unwound. And I'm interested in it because some of them are visible and others are not traceable. So the one that is barely visible, probably not without me telling you that it's there, but is visible, are these major channels in its skin, which allow it to collect water on its back in the desert, which then is filtered up through the channels into its mouth, so it never has to drink. Okay, so that's a kind of really interesting feature. But there are many other features here as well. There's a camouflage feature, which is very difficult to understand because it's in the desert. So why doesn't it have desert colors? Then there's micro relief here, and even little circular formations, which are, again, I've spoken to biologist friends of mine. They can't trace it. And the thing I like about that is that there's something that's performative about this. There's performance on many levels, but not all things can necessarily be traced to the path of evolution, the big arrow of evolution, which is optimizing things. Okay, and this is my new favorite. It's just this is a toucan. Again, funny to think about the biological understanding of the toucan. Over time, for a long time, the thing wasn't even researched. It was assumed that the beak was a kind of stand-in for the male organ, let's say, in order to attract mates. But then biologists took it on a little more seriously and said, okay, well, maybe that's the case. So let's look at the female birds. This is a male bird, and they found out, well, the female birds have just about the same size. So what's the deal there? Can't be that. And they said, oh, it's got to be the fruit, the size of the fruit in the jungle. So they looked at the fruit and they're like, well, no, not really. The fruit's pretty small. It's not the things that they eat. They don't need this huge beak. So it turns out that although those may have been some of the determining factors for the morphology, the features of the beak, the most viable and reasonable explanation for it is that it's a gigantic radiator. They've done thermal testing on it and found out that in flight that this thing is expelling all of its heat through a kind of radiant nose. I think that's great. So, because it is performative, but it's unexpected, and it also has a lot of other features that cannot be tracked. The color on the nose, I don't know. Okay, so some other objects of interest in the same vein, man-made. Let's say car design. Let's say armor design, wetsuit design. Interesting because, for instance, well, in the case of the armor, it's relatively straightforward, or not. It's clear that the pleats in the armor increase the structural performance of the armor. But again, it's also clear that the ornamentation produced through the pleating is as important. It's not clear which came first or how those things are in relation. Same with the wetsuit. The way that the seams are on the wetsuit and this additional kind of ornamentation or graphics on it are there based on maximizing mobility of the human body. But again, they're not all of the seams do that, and the same with this graphic stuff. That's not necessarily performative at all. Same with the Mazda Furai. It's all about wind and movement and air intake, but in fact, the air intake I heard from one of the designers is 5 times too big, and all of those micro pleats, which also have embedded LEDs in them, are not necessary at all for the wind flow. It turns out it's ornament. So I want to focus in on what we've been working on a little more specifically, and I was able to do that in two things. The first thing is that we're working on a threshold between surface and infrastructure, which is something that is a way for me of connecting spatial issues and issues of technology and engineering, both of which I'm interested in. So that includes articulating surface-to-strand transformations, and I'll show some of those examples in a minute, simultaneously revealing and obfuscating multiple systems, and reconsidering poché, the kind of black stuff in plans and sections. And then at the same time, my interest is in generating multi-objective composite assemblies, so you can have kind of combinations of things like structural color or ducted envelopes, radiant ornament, luminous hydronic thermal systems, things like that. So here's a couple of, I wouldn't even call these prototypes, these are just sketches, showing some of those kind of, or let's say the development of a grammar that we use in the office. And on the left you see a kind of transformation from a system which is trabeated into one which involves pleating so that you can have a structural performance, but also you can transport fluids and air for architecture. And then the other two, the yellow one and the purple one, are all about pulling armatures out of surfaces so that you can begin to have some kind of infrastructural behavior associated there in the top, and at the bottom a kind of exoskeleton which can increase performance of the surface by adding depth. We won't do that one. I'll show you the beam brain in a minute. So here's a few of these guys. We have this huge collection of these things, and it's getting kind of fun now. It's kind of a menu. Not that we order off of it, but they're collecting. I call it the menagerie. And if anybody speaks Chinese, I would still love to know if this says menagerie. I doubt it. It was published that way, and I still don't know. I heard something that it's not right. So it's the menagerie. It's the zoo of a lot of these species that we've been using for various projects. And now I want to show a couple of prototypes that are a little bit more in depth, which were developed in the summer this year, with an interest in, again, in developing multiple systems, developing it in prototype form, meaning in sort of a chunk rather than in a whole building, and also with a consideration of materiality, and in particular the place that we are in right now in history, which I would say is a very similar place to the one that Villers-le-Duc was in about 150 years ago, which is right at the moment where stone load-bearing construction was giving away to iron and eventually steel construction, which I found a kind of hybrid, interesting point in history. Also looking at, of course, aircraft construction, which is all about different kinds of patterns, aluminum, carbon epoxy, steel, everything known to man is basically in these airplanes now, with different kinds of configurations, and also produced, of course, by different companies. So the first one is called Thermo Strut, and Thermo Strut is a kind of combination of something which is a structural system, a skin system, an aperture system, and also something that generates thermal solar energy. So maybe I have a better picture here. Yeah. So this is still in the realm of frame and skin construction, but it does have a more active relationship between the frame, which is this custom welded steel profile, and the skin, which starts to relate to the profile. And then it also has embedded tubes for solar thermal, and then also other areas which are made out of composites, which also contain fluids that flow through it. So here's a model of it, and you can see here that there's also color associated with this prototype. So it's operating on many levels. It's generating thermal energy. It's structurally sound. It has apertures, and it also has this kind of ornamentation which ties it all together. This color and ornamentation that ties it all together. So some of the solar thermal is embedded here in these black tubes, and then also some of it's embedded actually inside of the apertures. So that's the first prototype. Another one is called the lizard panel. The lizard panel is basically a combination of an algae system. Algae systems are photosynthetic systems that can generate. Well, they generate oxygen as a byproduct, but they can generate biofuel. They can also generate hydrogen gas. They can generate a whole lot of different things depending on the additives that you put in it. The thing about them for me is that they're usually applied in a kind of industrial kind of application. And so the idea was to loosen that up, but also combine it with a water reclamation plant. So here's the model of it, where you start to get an algae system here embedded in the panel, which is a separate tube here than the surface. And then also these areas in the panel which can collect water, so these kind of depressions. There's the model. These kind of depressions that also wind around and through the algae system. And the most interesting thing about that for me is that if you try to understand the thing as two different systems interwoven, they're not just sort of laying on top of one another, but they're interwoven in such a way that that down below the panel, you start to get some structural performance by adding depth between the two systems. The third one is called tracery glass, and it comes from an interest in stained glass, and in a kind of combination of, or let's say not a combination, but a rethinking of the high tech. Let's say Renzo Piano, which used to his building in LA used to be right across from my office, so we looked at it all the time. And trying to deal with the layering of systems that goes on in a Renzo Piano building, or at least the one that was across the street from us, in terms of shading, in terms of cooling, in terms of structure, and then thinking about the beauty and the simplicity and the emotional response involved in stained glass, and trying to think of an alternative to kind of either or, where you have the purely ornamental and the purely technological, and so we came up with this. And what's going on here is that you've got a structural system. You have these apertures. You have they're bubbles, so it's a two-sided system where you can generate a lot of heat. That heat is picked up by coils here. So again, we have a solar thermal system, and then in addition, we've got a solar PV system right here, which is also embedded into the windows, and it's associated wiring and all of that. So you get through the deployment of these different technologies, you get some sun shading. You get a kind of impeded view out through the glass, so it's no longer a kind of modernist idea of glass. So I actually like the effect that it has these things embedded in it. And you've got these other things going on, this energy generation as well. So this also took on layers of color, which I liked very much in the sense that they could begin to dissolve the structure versus the polycarbonate panels here, and start to tie everything together in a much more loose and kind of gauzy way. Okay, so here's another project which is a kind of prototype. It was for an exhibition last year. It's called Batwing. Batwing came from looking at a lot of ceilings. I've gotten kind of obsessed with ceilings, in particular ceiling panel systems, and also fixtures. And I mean, here actually I was checking these out today. I don't see too many. At least you don't have too many air exhausts in here, but you do over here hidden. But I think that ceilings are something that were kind of left out of a lot of have been left out of a lot of discussions. Not because the ceiling is particularly important, but because the ceiling tends to be a place where a lot of fixtures are put in a kind of haphazard way based on building codes and so on, and never really dealt with architecturally. So I thought, this is an interesting place to start, also because there tends to be a lot of technology in ceilings, and kind of rethinking the air diffuser, the problem of the air diffuser, and also of the ceiling system. One example I found I think is again a kind of proto example of a new way of thinking about technology in the ceiling is a multi-service beam, which comes. It's not custom, but it comes with a cooling element and lighting and fire alarms and all that kind of stuff embedded in it. Although again, I think it's a kind of tool for engineers. It's not yet architecturalized, so that was the goal of Batwing. Batwing is based on a fluid system, a radiant system for heating and cooling, and a microcapillary system, meaning these tiny little veins filled with water. I think microcapillary systems are coming up. I think we'll find them very soon in a lot of architectural surfaces, so I wanted to take that on. So that's one component. The other component is a morphological component where through double delaminations of surface, we start to get hollows through which we can send air, at the same time increasing the structural performance of the kind of ceiling. So you see here how there's some air distribution going through this thing, which is then passed along this lattice of microcapillaries for heating and cooling. So you don't have central air. You just send air where you need it to go, and then you run it across for heating and cooling locally with this water system. And also, there's lighting associated with it so that you could actually see through. So this is, say, in the room, and this is from above. This thing doesn't, it's a prototype in the classical sense. It doesn't solve all problems. It doesn't have a particular scale. It's just kind of a study. So here it is. One important thing is the types of morphologies that are going on here. Again, you have the surface to pleat, so you start to register things in surfaces. Then you also have the surface to armature, where the pleat actually begins to pull off and become an armature. And then you have these microcapillaries inside of microrelief on the surface. So this stuff is as, if not more important than the technologies that are embedded in it. Here's some pictures of that prototype in my office. We had it made in China, of course, and at the show. Okay, so here's a quick building project to show maybe an application of Batwing at the building scale. This is a project that I did with Yansung Ma at MAD. He was actually the client and the master planner of a pretty large development in Guiyang about a year and a half ago. And it involved a lot of high-rises. So our project was a high-rise, 110-meter building, and the idea was to take on a kind of dual. There was a dual interest there. One in taking on mechanical systems, starting to architecturalize them, but doing so in a way that does not continue the structural expressionist movement from the 80s, but doing so in a way that is much more contemporary and allows for a kind of gauzy, lighting, luminous kind of effect in addition. So here's the basic technology of the thing. It's intended to be a series of super columns around the project, which take structural forces, deal with lateral, also deal with obviously with the movement of air and pushed through by the stack effect. Then there's another system, which is a system of microcapillaries, which is about expelling heat. So the idea here was that instead of having a condenser on the roof, like all high-rises have, It was to unwind the condenser in a way and kind of spread it all over the architectural surfaces as a gigantic heat exchanger. So that was as an alternative to a kind of conventional system using risers and ceiling ducts and all those things. So yeah, here's one of the floors. We had a computer floor here. This is what they love in China, these access floors. And the idea is that the super columns are so high and so long that that you don't need any fans or anything. It's just through its own suction and basically the chimney effect, the stack effect. The air is brought out of the building and exchanged, and then the cooler air is brought in. In plan, you see how one of these double delaminations might work. In this case, it's not just a single kind of prototype material, but it was broken down into a facade here, which goes around and becomes a megaplete, and then a structural member, which is a precast concrete member in the back, which has holes through it in order to get the air into the, just local at the floor level, get the air into the ducts. And then there's an additional outer layer, which is perforated, which allows for a kind of, again, that kind of gauzy effect. So you don't read necessarily ducts on the exterior, but you start to understand the thing as a whole composition of lighting, structure, mechanical systems. So yeah, so here's the thing at night. Tied to the lighting effect is the actual temperature of the air that's moving in different times of year. So that would be a kind of changing effect. Okay. Different project. This is from a couple of years ago. It's called the Novo Pavilion. It was a competition, and it comes from an interest in combining a kind of a grid-stiffened shell logic with alligator skin, or let's say variability in alligator skin that goes from it's actually very much like the Dragonfly. It goes from quad cells, which are armored and very stiff, to elliptical and round cells, which are all about flexibility. So trying to apply a kind of more biological logic to something which is a kind of important architectural type, the grid-stiffened shell, or lamella construction. So here's a first study of how that might work. The thing that we were going for was a lot of difference inside of the system that could respond to different factors. This one doesn't have depth variability yet, but that's one of the factors that change. The other factors are going from a grid to a kind of branching system to even a radial system in some areas. So the intention was to have a much more radical difference in the pattern. So here are some studies, some of which are relatively straightforward. They key pattern to curvature, so you have a lot more breakdown of pattern where there's more curvature, and then you don't in other areas. And then other ones have a lot more work done on them by hand and also with the engineers as to what are the main force lines and what are we going to concentrate on here. A kind of editing of a natural panelization that comes out of the software we are using. So this is the project. It's really just a pavilion. It doesn't have a complex program. Interesting here is the shape, and not just the pattern. The shape was critical for holding the building up. So what we have is a slightly arcing roof, but it's characterized by these two large vortex-like areas, which basically add double curvature to it, which increases the overall stiffness. So they're like two gigantic super columns organizing the space and also acting structurally. So this pattern on the roof, again, is a pattern that is an architectural pattern. It's not just a response to particular parameters relating to surface curvature or engineering parameters, although those are taken account of. It's also a pattern that was that is precisely designed for a certain kind of character. There's depth variability in the system as well. This is the elevation, and from the top. So this is a similar project. It was done a little bit later, but it has some of the. I guess it builds on Novosibirsk. It was for Sundsvall. It was a competition for 2 theaters in Sundsvall. One of them is a concert hall, and the other one was an opera. And this project also interested in relief, interested in structural variability, and in this case, we wanted to take the idea of shape of the overall thing to a new level, which in this case was to make these involutions more interconnected, and also force them to do more work than just structural work. So they actually go inside and become the circulation of the building. You can see here. These are the theaters. So this thing's a kind of topological continuity from inside to out. The theaters are right here, and then it sucks back around like a Klein bottle onto the exterior, and which also happens to provide a main loop of circulation from the ground level up into the two theaters. One important thing for this was, again, competition done very quickly, but with Barreau-Happold on this one, and really fun to work with them. And basically, we set them the task of doing the fastest structural parametric model of all time. So we sat down, and in an afternoon, we decided, basically, with some very unrigorous structural analysis, we decided the main force paths going through the structure, and then some secondary zones where we needed additional depth to the structure. So we used this as a basis for further modeling on the project. We added some control lines so that we could add depth variability to the structure. We also associated window openings with depth variability, as well as with actual views outside of the building. So it wasn't a one-to-one relationship where we have deep structure, we have windows, but that was one of the ways that we started to associate things together. And then there was this idea of having the interior switch in terms of kind rather than just degree. So in other words, sometimes we have a shell construction with some relief in it, which then skips and becomes a kind of truss network in some areas where we need additional spanning. So this is where it gets kind of interesting, where you're not just increasing depth up or down, but you're actually switching systems from a shell-based system to a vector-based system. And in addition, we added the layer of color to that to make that more intense. Okay. So this is a. How am I doing, Theo? What time is it? I'm gonna just keep cruising here. Would help though.
It's 10 to 10.
10?
Up to the 8.
I'm totally asking the wrong guy. The other jet lag guy in the room. Yeah. Okay. Okay. So this is Dragonfly. It's based on what I mentioned before. I described the wing already and the kind of dual morphology. And I did Dragonfly with Barreau-Happold, and we had endless discussions about this project, which was quite fun. The Great Court for Norman Foster. They also did, I think, a more interesting building, the Smithsonian with Norman Foster, which takes on some of the logic that we were working with. But basically, the idea was to search for variability in the structure that would increase the performance of the project, but also increase the aesthetic characteristics of the project. So this is not about engineering optimization per se, although there was engineering done on this one at a higher level than the competitions. So we used this idea of beam brains, which was, again, to locate areas. We took the logic from the grammar from the Dragonfly Wing, which is basically the quad cells, which are also folded areas in the wing, versus these membrane areas. And we decided to, again, we weren't interested in reconstructing a Dragonfly Wing because clearly that is all about performance in the air. So this thing is not about that. It is a canopy project, but it has multiple points of touching down inside of the gallery here. This is the SciArt gallery, and it was an exhibition there. An installation. And you can see that we basically started in the middle of the gallery, and then we started to work outwards from the middle and grab onto things that were available structurally. So there were only a few things. There was a mezzanine in the back, which was a steel mezzanine. There's a concrete column. And then there are a few other things. They tend to be in the back. This is a big sheetrock wall, which we couldn't put any loads into. So it ended up being a kind of a setup. We forced the thing to cantilever 50 feet with a 10-foot backspan, just to see what would happen when extreme forces are running through the thing, and how it would begin to reorganize morphologically. So here's how it's connected in the back. There were several boundary conditions applied to this thing in ANSYS, which is a population generating software. And one of them was cell size, there was cell density, there was overall depth, and then the local depth. And there were various other boundary conditions applied to this thing, which started to differentiate it more and more. You can see there's an early version of it versus a later one, and I want to point out that the process took 2 months of engineering, feedback engineering, and some of the parts about it that I really got excited about were these areas that came from the engineering software. First of all, the reorganization of a lot of the membrane cells towards the center of this thing where there's some vaulting. And then also some hybrid moments again where you start to get linear elements which are somehow related to the quad cell areas, but which actually begin to run through the membrane. So you get these hybrid areas which are emerging out of the interrelationship of both the shape and the pattern logic. I'm going to cruise through some of these here. That's not so interesting. So this thing was also done in CATIA, which was a learning experience for me. So this is the parametric plan that we got out of CATIA. So it was always being updated based on the engineering. Very, very easy to update. All of the leaders and notes and angle information, all that was constantly updated as we worked on it. Thank God. And here you can see, this is also, I think, one of the more interesting parts of the project. You can see where we also, as a final boundary condition, as a kind of way of fine-tuning the structure, we developed a construction system where we could layer material. So this is all 1/8" aluminum, and there are some panels which are only a single layer, and then others which are 4, and then there are extremely thick areas which are up to like 11 or 12 layers. So again, the idea wasn't to throw material at Dragonfly to make it work, but that was a kind of final way, after dealing with shape, after dealing with pattern, after dealing with all of the ways of refining the architecture of the thing, to just make it work. But that also had a nice quality as well. And then here you can see, of course, in CATIA, you can visually pull all these panels apart so you can tell the difference in how many layers they are, and then these are all the bolts, and these are all the angles and all this stuff that you need to build it. So there's a packing algorithm that we used. So there's the piece. I was a little sad about all the bolts. We were going to do structural adhesive. Engineer didn't want to do it. So here it is. You can see really big differences in depth. Some vaulting here. This is a delamination. You can't see the top leg of this thing, but it's been delaminated, and the leg is grabbing top and bottom on that side. Here it's grabbing up in the corner and then underneath the mezzanine. Okay, so I'm just going to keep this up. I need another 15 minutes, guys, so bear with me. This is a much larger project, but it was a chance to take the Dragonfly logic to a building scale, which was always its intention. This is called the Garrick Market in Seoul, Korea, and it was done together with Changzhou architects in Korea last summer. And I think you guys did. I think the students did a fish market here. This thing is also a fish market. It's the biggest one in Korea. Really interesting building type. It's sort of accreted over time, and the idea from the government, from the mayor, was that we should offer more green space, number one. Number two, that we should ameliorate the smell of fish, and number three, that we should offer some kind of public functions. So the first idea with the local architect was to take a lot of the market here that's close to this canal and double it up on the market in the back to open up a wetlands area. Probably the reason why we lost the competition, I think, in retrospect. But this was the main move, was to double up the size of the levels of the market and have trucks accessible to 2 levels of market. Then also we wanted to propose a kind of roof landscape to get rid of the problem of the fish. at least the visual problem of all the fish guts and all that stuff. And then we wanted to offer this community garden to all the people living around here. There's about 60,000 families, and we thought it would be nice if as part of this roof structure, that we could offer these little micro gardens. So we thought about patterns of patterns and flowers and vegetables and all these kinds of things. So organic material, but also a structural principle. And the structural principle was based on dealing with the fact of the matter in the market, which required a very ruthless and rigorous column grid, and then an area which would begin to be more loose and open-ended, and also cantilever out. So that's how we set up the pattern. The thing is about 1,000 meters long. It was a pretty big project. So the ground level's relatively straightforward, tons of market. And as you move up, you see that, in fact, the thing is organized by extremely mega elements and then very micro elements. And it was asked that we put a kind of a shopping mall on the roof of this thing. And it wasn't clear how to do that. We were first just going to kind of litter the roof with a bunch of buildings, and it didn't make sense. So what we decided to do instead is again offer some kind of mega pleats, some double pleats in the roof that would allow us to kind of allow the roof to ingest the shopping mall. So you get these gigantic beams in the roof, which are also spatial, which also allow people to be up inside of the roof looking down and understanding the market and all of its functions without actually being in the market, and then also have access up to the roof and those kinds of functions. So, well, there it is. That's probably the best view. I don't think I'm going to show this. I'm going to skip ahead. I don't know how to do that. I'll just skip ahead. Okay, I'll just say really quickly, this is PS1. This is one of my oldest projects. It involved a kind of cellular structural system, and it was clad by a skin which was based on parabolic and conoidal geometry made out of expanded aluminum mesh, which, when rotated in different directions, allows you to have a day and night kind of effect. So if you rotate it one direction, you pick up light, and you rotate it the other, and the light goes through. So during the day, it's a huge shading mechanism, and during the night, you actually begin to read the structural cells, some of which were up to 50 feet long. Okay. Last couple of projects. This one was a competition in Taipei, which was last year. 3 theaters in a really great site in Taipei, and a pretty strict brief. The brief basically said that you need to, this is the site, and this is the main railway, and this is the Shilin night market, a kind of really interesting farmer's market that's open at night. And so the brief asked that you enter from this side, so that was kind of a given, and that also that the building has a really tight connection to the Shilin market. So we decided to bring in some of the qualities of the Shilin market into the building, into a kind of concourse inside of it, and at the same time lift the building up to allow for this kind of big public entry. So the project here was generated out of a really large surface, which then started to have mega armatures hanging down below it, which acted to connect the 3 theaters. There's 1, 2, 3. This is the gigantic theater, in a kind of a concourse, which so a kind of a structural bridge connecting all of the parts together, but also acting as a gigantic ceiling scape to the public space below. There's the plan. That's some of the. You can see that there. This is a view from directly below. You can see that there are these apertures that run all the way through, all the way up to the roof. So you've got a kind of composite here of kind of ornamental elements, a structural system which is spanning between the 2 sides, and all of these pedestrian pathways, these gigantic armatures, and then in addition this kind of color gradient. So here you are underneath. That one's not so bad. We also got this was kind of a mistake in the way that we were doing the color, which we really liked. It looks kind of like an Aztec pattern. Really nice. So here's the main view from the entry from the railway of the project. And I want to show just one last project. Skip ahead on this one. There were... Okay, so there's two bioreactor projects. I'm just going to show the very last one so I don't keep you guys longer. Bioreactors came out of a collaboration with Origin Oil. They're a company dealing with algae products, and they're really hell-bent on moving past the oil economy. Really interesting guys, also located in LA, so it's very convenient. And they have all kinds of technology, which I guess they don't realize the potentials of it. They have a bunch of guys in a lab, and it works quite well. But I guess when I was going over there, I guess I realized the extent to which they didn't know what they had. So we started to talk about these bioreactors and what we could do with them. And this one in particular is interesting. It involves a tuned LED system that actually can begin to sense the needs of the algae. So that you can maximize the production of lipids from the algae. If people don't know about algae bioreactors, basically the idea is that you take a pool of muck, you give it some sunlight, or in this case artificial light, and it produces lipids. Lipids are a kind of vegetable oil, and you can refine that into a usable oil for biofuel. So it's actually a huge industry. It's exploding right now. It's completely overtaken wind, solar, and ethanol. So I think algae is going to be huge in the next century, for sure. But I mean, I'm interested in that, but more so in the kind of architectural effects that you can get from this as well. So in this particular system, and they have several, you've got these tuned LEDs, which can sense the needs of the algae and adjust based on intensity of light and also color of light. And I combine that with a public art project that I was asked to do. This is kind of a weird side picture, but this is in downtown LA, right next to the Lakers Stadium. And this site is almost impossible. It's a kind of narrow walkway with trees on one side, a brand new glass facade on a warehouse building, and then this strange awning. And so the idea was to take what we learned from Origin Oil and try to recompose it in this site as a piece of temporary art. So here's the project. It's a kind of micro and macro pleated facade element that is inserted into the glass facade. It's a kind of algae aquarium, and it's also got this stuff coming off the sides of it, which continue down the glass facade, which is kind of a kind of tongue-in-cheek ornamental element coming off the side, and then this element which I really quite like, which runs across the soffit of this overhang and then up the tree, and we call these the tree monkeys. The tree monkeys basically climb up the tree and then have a few solar panels which run the pumps that are required to circulate the algae as well as the lighting. So there's some sections through the thing. It's actually quite deep in some areas, about this deep. And here's a model of the insides of it, showing some of the articulation of the pipes and tubes in the algae system. There are the tree monkeys. And at night, the really interesting thing about it is that it actually has, as far as I can tell and as far as Origin Oil says, it's going to have a kind of firefly effect where it'll pulsate. Probably this is sped up, probably much more slowly than this. But it will have a kind of feedback loop and very atmospheric effect, but at the same time be producing biofuel. So I think I'm done. In more ways than one. Yeah, I'll take a couple questions and then we'll wrap this up.
Is there any questions for Tom?
Everybody's tired.
Silly question, I have to. Tom, I'm surprised you didn't reference Bionicles. I just have to ask this because, especially in the kind of latest projects, there is this. I mean, I love obviously the iconography of that kind of thing, and also Japanese comic books. Does that has any kind of impact on your work?
Yeah,
it's a very light question.
Yeah, no, fair enough. Well, this is something that we've talked about before, but yeah, Bionicles. For anybody who doesn't know what that is, it's a kind of Lego set, kind of manga Lego set. No, I don't think that's a direct relationship, but the thing is that as you know, I also have another business that runs in my office, which is a rapid prototyping business. We do work for all kinds of people, mostly Hollywood stuff, and so I'm noticing that there's starting to be a kind of infection from a lot of those projects. We indeed do have Legos at the office. We have stuff that we did for various movies in there as well, which people are probably familiar with, and it's getting kind of interesting because I think that I'm straddling now a bit. One business is intended to support the other, and it's not the architecture supporting the other one. Let's just say that. So, but when you make choices like that, I think you're also opening yourself up to all kinds of things, the unexpected things. So I will take responsibility for that. Although not for a kind of cartoonish aesthetic. I'm not interested in that on that level, I would say. But fair enough. Anybody else? No? Okay.
Then we'll leave it here.
I think we're done.